Hello engineers, welcome to the new video of the course. And in this in this particular video we are going to focus upon the common source stage with a current source load. So basically till now we had just focused upon what exactly a current source and how exactly we can design a current source with the help of a single MOSFET, and we concluded that whatever the MOSFET may be, whether it is a PMOS or a NMOS, if we are operating it in the saturation region, and when I say that my single MOSFET, it acts as the current source, right? We can easily replace it with a single impedance equivalent to RO. So this is what we concluded in the previous video. So till now we had just focused upon the current source. Now from this particular video we are going to focus upon the application of the current source, right? Where we are going to use a current source, and whenever we use it, what advantage we get when we use a current source with the help of us which is made up of a single MOSFET. Okay, so just make sure that right now we are just focusing upon the application part. Okay, so that doesn't mean that in this video only I'm going to show you the application or the advantage of using a current source, right? When we simulate the when we are going to simulate this particular circuit onto the LTSpice software, right? After simulation I will be explaining you the advantage of this particular circuit, right? We'll see that in real world. Okay, so don't worry about it. As of now we are just going to focus upon this particular circuit. So we have already seen this particular circuit. What is this particular circuit? It is a simple common source amplifier. What we are doing, we are just giving the input voltage to the gate terminal, right, or the gate source terminal, and then we are taking the output voltage at the drain terminal. And we all know if we provide a weak AC signal, we are getting a strong output signal, but it will be inverted in nature. Okay, so we have already revised it in the previous section. Now what if I tell you that instead of this particular RD we are connecting the constant current source? Okay, what if I tell you that instead of this particular resistor RD we are connecting a current source? Now you might think that why exactly we are doing so. I'll come to this particular point later on, so don't worry about that. Just imagine that instead of RD we are connecting one constant current source, and when I say that I'm connecting a constant current source, you just focus over here. This current source or this particular current, it is moving from VDD to certain node, right? I'll just highlight this particular point so that you should not get confused. I had seen most of the guys getting confused over here itself. So this is my node. So my current ID, or basically constant current source, it is moving from VDD to certain node. So over here, what should I connect? Should I connect NMOS or should I connect PMOS? Just pause this video, take your own time and try to think in your mind that should I connect NMOS device or a PMOS device? Take your own time, pause the video. Alright, I believe that you all guys have tried your best. Now it's my turn to explain. So we had clearly seen this particular concept in the previous video. You can clearly see over here, this is my current source. It is present in between VDD and certain node, right? VDD and certain node, right? If you want, you can check this as well. Current source, it is going to ground, no. So this particular condition won't apply over there. So yeah, this condition, it suits well, right? So basically we can replace that particular current source with this particular model, that is PMOS. Okay, so this is how the circuit will look like. So you see this particular current source, it will be getting replaced with a PMOS device. Okay, so this is a PMOS device. You see this will be my VDD. Okay, the negative terminal, it will be connected to gate, the positive ones to the VDD, to the source, my bad. Okay, let's say this is my M1 and this is my M2. Okay, and we are taking output in between M1 and M2. Okay, you see this particular part, it is exactly similar. Okay, just have a look. This particular part, it is exactly similar. And again, as I clearly mentioned, I'll be playing with symbols, okay, because I want that you all guys should get confused, right? So this is an NMOS device and this is also a NMOS device. Okay, few of the students till now they might be getting confused. Okay, even at this particular point as well, few of the students might get confused, but this is what I want. You should get confused. Okay, this is the first step of learning. Okay, just have a look. This particular part is exactly similar, right? this particular part over here as well, it is exactly similar. What we are doing, we are just playing with the upper part. Okay, what we did, we had one resistor RD. Instead of RD, we are connecting one current source. Now we will come to that particular part, that what advantage we get when we connect a current source over here. Okay, we'll come to that particular part later on. Just as of now, just listen to this particular point very bluntly. Okay, then what we know is that this particular current source can be replaced with a PMOS device or a PMOS model, right? Great. Okay, so this is how the circuit will look like, and what we know is that this particular circuit, that is a PMOS operating in the saturation region, that means a PMOS acting as a current source, can be replaced with a simple RO. Okay, simple impedance equivalent to RO. Okay, so you see this particular PMOS, it was acting as the constant current source, it got replaced with a simple impedance equivalent to RO. Okay, so again, if you want, you can just go through this particular point. You see there is this particular constant current source. Okay, what we did, we just replace it with the PMOS. Okay, and then this particular PMOS, we replace it with a simple impedance equivalent to RO, because right now we want to see what exactly is happening when we are dealing with a small signal. See, this Vn will be a small signal. We are providing certain input voltage, let's say of 1 millivolt, 5 millivolt, or 1 microvolt, 5 microvolts, right? So we need to check how exactly this particular circuit behaves for small signal. Okay, so right now we are dealing with small signal analysis, and for that very purpose we are just replacing this particular PMOS with what? With a simple impedance equivalent to RO. Let's say this is RO2. I just forgot to mention this. This will be your RO2. Why? Because this is your MOSFET M2. Okay, just remember this particular point. If you want, you can just take a screenshot of it. Alright, I believe that you all guys have taken a screenshot of it. Now we will be dealing with its AC analysis. That means we'll try to calculate its gain, alright, its impedance, input and output impedance, and then we will also try to find out certain conclusions out of it. Okay, so let's proceed further. So this is how your AC model will look like. So you see your this particular MOSFET, how you are going to draw the AC model of this. I'll just draw it very quickly. So this will be my gate, right? This will be my source. Okay, and it will be grounded, because you see the source terminal, it is grounded, right? So this will be grounded. I'll just draw over here very quickly so that you should not get confused. And obviously we know that a MOSFET is a voltage controlled current source, so a current will flow from drain to source. So this will be my drain terminal, and the current ID will be equivalent to GM times of VGS, right? So basically we have drawn a small signal model of this particular MOSFET, that is M1. Okay, and it is not completed yet. We just need to show RO1. So this will be my RO1, the impedance of the MOSFET. Impedance offered by MOSFET M1 is RO1, and you see over here, okay, to this particular drain terminal, there is this particular RO2. Okay, it is connected to ground. Why? Because in AC analysis, as clearly mentioned, we short circuit this particular part. Okay, we short circuit this particular part. That means during AC analysis this will be grounded. Okay, just remember this particular point. During AC analysis this will be grounded. If you want, just have a look at this particular image. That will surely help you. One sec, let me just check if I have shown that. Yeah, something like this. Yeah, this should be VSG, this should be VSD. Okay, and then that gets replaced with a ground. Basically they will be short circuited. Okay, I hope this particular point is absolutely clear to you all guys. Let me move over here. One sec. Yeah, so RO2 is connected in between drain terminal and ground. Okay, so RO2, let's say this is my RO2, one sec, RO2 is connected between drain terminal. So this will be my drain terminal, okay, and ground. RO2 is connected in between drain terminal and ground. This is what I have shown over here. So this is how the entire model will look like, and obviously we have connected, you see, we have connected the input voltage to the gate terminal, okay, and the other part of the input voltage is grounded. So this particular gate terminal, it is connected to the input voltage and the other part is grounded. So this is how your entire model will look like. Okay, and that's what I have shown over here. Oh, and this will be GM1 VGS1 because that's for M1, right? That is for M1, right? We're dealing with M1, so that should be GM1 times of VGS1, right? So over here as well, this should be VGS1. My bad. So over here, this should be VGS1. Let me just write it properly. Yeah, this will be VGS1. I hope this particular part is crystal clear. So I'll erase this part. I hope you understood how we got the entire small signal model. Again, I'll just quickly revise it. So yeah, you see over here, this was my MOSFET M1. So we drew the small signal model of it from gate to drain, right? This will be your MOSFET, small signal model of MOSFET. We just named it as VGS1, GM1 and VGS1 because we are dealing with M1, right? And after that, we saw that over here, over here we have RO2. What is this? This is the impedance offered by this particular MOSFET M2, right? So we just need to connect RO2 in between drain terminal and ground, right? So you see I have connected RO2 in between drain terminal and ground. That's it. And then we are taking output from the drain terminal itself. So you see we are taking output from the drain terminal itself, right? And we have this input voltage connected in between gate and source. This is what I have shown over here. Input voltage connected in between gate and source. Source is grounded, so that's why input voltage, the other terminal of input voltage is also grounded, right? I hope this particular part is absolutely clear to you all guys. If this is clear, then we can easily proceed further. Let me just move it down, shift it down, so that whenever you will refer my PDF, it will be pretty easier for you to understand the things in depth. Okay, now let's proceed further. Okay, so now first of all we'll deal with the output impedance because it is quite simple. If you see what will be the output impedance offered by this particular model. So for output impedance, short circuit the input voltage according to the Thevenin's principle. So what will be my output impedance? So we try to look output impedance from this particular terminal, that is, this will be my R out. Let me just draw it properly. One sec, let me use this one only. This is how we try to look the output impedance from this particular terminal, right? I hope this particular part is crystal clear, right? We have done multiple analysis and we have also seen we have also seen a lot of numericals based upon this particular idea. So I hope you know how to find out output impedance. So what is my R out? So if you look at this particular point, my input is grounded, right? So my VGS will be straight away 0, and if my VGS is 0, so the output impedance will be RO1 parallel with RO2. Why? Because this particular part, it will act as what? It will act as an open circuit. It will act as an open circuit. Again, I'll repeat this particular point. See, we short circuit the input voltage, okay, during this particular concept. Like whenever we try to find out the output impedance, we just short circuit the input voltage according to the Thevenin's principle, and then what we get is that my VGS is straight away 0, and if my VGS is 0, VGS1, my bad, again I just did a small mistake over here and I'm extremely sorry for that. So this is my VGS1. So my VGS, if my VGS1 is 0, so this becomes 0. That means what? My drain current ID, which was flowing from drain to source, that becomes straight away 0. And if my drain current ID is 0, so what does that implies? That states that it implies that there is an open circuit over here, right? And it's like RO1 in parallel with RO2 in parallel with the infinite impedance. So this offers infinite impedance, right? So what will be my output impedance? So my output impedance will be, just write over here, my output impedance will be R out will be equivalent to RO1 in parallel with RO2. So this will be my output impedance. I hope this particular part is absolutely clear to you all guys. This will be my output impedance offered by this particular circuit. Which circuit? One sec. This will be the output impedance, that is the impedance offered by this particular circuit, okay, or this one or this one. It is one and the same. Let me change the color because I generally prefer to show the impedances in one sec. I generally prefer to show impedances in green color. So let me just change the color. Okay, this looks fine. Okay, now let's proceed further. Let's try to focus upon the output voltage. What kind of voltage we can get? Output voltage we can get. because you see over here, one sec, I just forget to show input voltage. So this is my input voltage. Now if I try to apply KVL in this particular direction, if I apply KVL in this particular direction, right from ground to ground, so what will I get? So you see this is my V in, this is minus and plus, let's say this is minus and plus. So plus of V in, this is plus and minus, we always take the opposite sign, minus of VGS is equivalent to 0. So what will be my input voltage then? So my input voltage will be equivalent to VGS. Okay, just make sure to highlight this particular point, it is very important. So my input voltage is equivalent to VGS. Great. Now let's focus upon the input impedance, and we all know that as gate is isolated from source and drain, one sec, let me just show it to you. What will be my input impedance? R in, technically it will be infinite. Okay, ideally it will be infinite, but practically we will get certain value, so we don't focus upon the input impedance, we rather prefer to mention it as, that is R in as infinite, okay. So I'll just put it somewhere over here, and I'll just change its color to green, one sec. Yeah, so the input impedance is infinite. Practically we will get some huge value, but that's fine, we can consider it as infinite, no need to focus on that particular point. So now what we are left with is voltage gain. We really want like what voltage gain we will get from this kind of circuit. Okay, for that we know that AV is equivalent to V out by V in, right? So we have the value for V in, we don't know V out yet. So V out is this. What will be my V out? So first focus upon the circuit. Let's try to find out the output voltage V out. So output voltage V out, it will get reflected over here as well, because you see RO2 and RO1 they are in parallel, right? Because you see RO1 it is connected in between drain and the source terminal, but the source is grounded, right? So RO1 and RO2 they both are in parallel, and voltage reflecting across RO2 is what? Voltage reflecting across RO2 is V out. So as these two resistors, that is RO2 and RO1, they both are in parallel, right? RO2, let me change the color. This RO1, what we know is that this RO1 it is in parallel with RO2, right? So same amount of voltage will reflect over here as well. So basically V out will be common for RO1 and RO2 because they both are in parallel, right? They both are in parallel, so same voltage will reflect over here. Okay, that is V out. Let me just put it somewhere over here so that you should not get confused. Same amount of voltage will reflect across these two resistors because they both are in parallel. Great. So what will be the then what will be the current? Okay, what will be the current flowing through this particular part? It will be same, I out. Okay, it will be same, that is I out. So I out will be equivalent to GM times of VGS. One sec. So let's say this is my current I out. It is flowing in this particular direction than in this one, and same amount of current will flow over here. What is this particular current? It is I out. Let's assume that this particular current is I out. What is I out over here? What is I out over here? So if you see over here, the current flowing in this particular direction is GM1 times of VGS1, and same amount of current will come over here, that is I out, which is equivalent to GM1 times of VGS1, and then you see same amount of current will flow in this particular direction or across this particular through this particular resistor, right? GM1 times of VGS1, right? So what will be my I out? It will be GM1 times of VGS1. I hope this particular part is crystal clear. Okay, I hope there isn't any confusion over here. Okay, so what will be my V out? Let me just show it to you in this way. So my V out, one sec, V out is equivalent to I out times of R out. What is my I out? I out is, one sec, I out is what? I out is equivalent to GM times of VGS1, but you see over here this I out, that is GM VGS, let me just write over here GM1 VGS1, it is flowing in opposite direction with respect to V out. We are trying to see the output voltage from drain to source, right? If I want to check the output voltage, what I'm going to do, I'm just going to connect one multimeter or voltmeter over here, okay, in between drain and source. But what I can see is that this particular I out, it is flowing in the opposite direction, right? So that's why I need to include one negative sign over here, because my current is moving in the opposite direction, right? So minus of, let me just change the color first, yeah, minus of, because as my current is moving in the opposite direction with respect to the output voltage, so this should be GM1 times of VGS1, right, times of what is my R out? R out is nothing but RO1 in parallel with RO2, right? RO1, let me use the green color, yeah, RO1 in parallel with RO2, right? So this will be my V out, this will be my V out. Let me just highlight this particular point as well. This will be my V out. Let me just move it down and let me just highlight it with some red color. Yeah, so this looks great, this looks fine. So now that we have the value for V out and V in, we can easily calculate the voltage gain. So what will be my voltage gain? It will be my voltage gain AV is equivalent to V out divided by V in. What is my V out? It is how much? Minus of GM1 VGS1 times of R1 in parallel with RO2, and V in is again over here I just did a small mistake. This should be VGS1, right? So your V in is nothing but VGS1. Okay, so one sec, let me change the color. This should be VGS1. Okay, so V in is VGS1, V in is VGS1, and this was minus of GM1 times of VGS1 times of RO1 in parallel with RO2. Okay, minus of GM1 times of VGS1 times of RO1 in parallel with RO2, right? And yeah, I just need to extend this particular line, and this is my V in, that is my VGS1. Let me change its color to maybe blue. So yeah, what can we see? We can clearly see that VGS1 and VGS1 they get cancelled, and what we are left with is this. So basically what is my output voltage gain? My voltage gain AV is equivalent to my voltage gain AV is equivalent to minus of GM1 times of RO1 in parallel with RO2. Okay, so this will be my voltage gain. Let me just highlight it. Okay, so this will be my voltage gain. Okay, now if you could remember what gain we used to get in this particular circuit, what was the gain for this particular circuit, right? So if you could remember, the voltage gain for the simple common source stage was AV is equivalent to, it was equivalent to minus of GM times of RD in parallel with RO of this particular MOSFET, right? So the gain, sorry, this should be minus, okay, minus of GM times of, let me just shift it to right so that I can include the negative sign. Yeah, so you see the gain remains constant over here as well for this particular circuit. Instead of RD we have RO2, right? But there is some drawback for this particular circuit, and what it can be, just pause this video and try to think. Alright, I believe you have thought upon this particular answer. Now it's my turn to explain you. So if you could remember, in the common source stage, I guess in the previous course I clearly mentioned that the RO, this particular RO is very high as compared to RD. Let's say if your RD is how much, let's say if you keep this as, let's say 10k, this RO is approximately this RO is approximately equivalent to, let's say, maybe 100 kilo ohms or even greater than that. It totally depends upon the MOSFETs and the lambda of the MOSFET, okay, channel length modulation and all. But you see, RO is very, very high as compared to RD. So with this particular equation, we will be able to achieve the gain, okay, the desired gain, okay. But this, with this particular equation, you see, with this one, sorry, with this particular circuit, my bad, with this particular circuit, the equation that we get is this, that is RO1 in parallel with RO2, right? So with this particular circuit, we are able to achieve some higher gain. Okay, so let's say I'll just take one rough example with this particular circuit, right? With this particular common source stage, if we are able to achieve the gain of, let's say, 10, so with this particular circuit, we can easily achieve the gain of 100. Okay, so you don't need to play with the value of RD. And let's say even if you increase RD, so there is a chance that you can actually play with the biasing voltage, right? So you can shift the biasing point, and in that case you can easily migrate from saturation region to the maybe cutoff region or maybe to the linear region. So there is that probability, right? So there is that kind of disadvantage. Even if you increase RD, you might lose the saturation region. So there is that particular probability with this particular circuit. But yeah, just by connecting a simple current source, you can easily achieve much higher gain as compared to this particular circuit, right? Not necessarily 100. I have just given you a rough example so that it's pretty clear in your mind. Okay, I hope this particular part is crystal clear, and that's the advantage we get with the current source load. I hope this particular part is crystal clear. Yeah, we have not seen the actual simulation part yet. We'll see that, so don't worry about that, but that's the overall idea. Okay, and let me just write the pointers which we got over here. R in is infinite, right? R out, what was my R out? R out was RO1 in parallel with RO2. R in was infinite, and V in was equivalent to VGS1. Sorry, let me just change the color. V in was equivalent to VGS1, and V out was equivalent to minus of GM1 times of VGS1 times of RO1 in parallel with RO2. That's it. So this were the few of the conclusion which we drew from this particular circuit. I hope this particular part is crystal clear, and most important thing was that the gain offered by this particular circuit is much higher as compared to the common source amplifier or common source stage. So this is the key point. Let me just write this particular point over here. Okay, what is the conclusion we draw from this particular circuit? The gain offered by this stage or by this circuit, whatever you want to write, is much high as compared to common source, as compared to simple common source stage. Okay, this is the most important point. Okay, we are going to verify that with the help of simulation, so don't worry about that. But I really hope that you understood and you enjoyed this particular point or this particular session. Okay, what I'll do, I'll just end this video over here, and in the next video we will solve one numerical based upon this particular idea, and after that we will simulate this particular circuit onto the LTSpice software, and then we will verify whether the findings which we got over here, that means the gain offered by this particular circuit was high as compared to this one. We'll verify that particular findings, right? And now I hope you at least got a brief idea that what a current source is and what it is capable to do.